Assalamualaikum. Good morning everyone. So today, okay ke? So dah nampak slide saya? Everybody?
Nampak.
Alright, good. So today we're going to continue our presentation, our class, Synchornous class for the air conditioning process, part 2, which is previously we have looked on the processes that involve with the simple heating, simple cooling, heating with the humidification to add moisture content, and then as well cooling with dehumidification to take out the moisture content from the environment. And then today we're going to look a few more air conditioning processes, which are, first we're going to look on the evaporative cooling. Just going to go briefly on the evaporative cooling, and then the next one we're going to look for the adiabatic mixing, and then finally we're going to look for wet cooling tower. So I hope that you have followed all of my YouTube classes that I have uploaded before, and if you don't have time to look on that videos, please do so before you submit your coming due assignment. So hot air enters the evaporative cooler and then sprayed with the liquid water, and then part of the water evaporate and then absorb heat from the air streams. The air streams decrease and it increase the air stream temperature will be decreased, and the humidity will be increased. So adiabatic saturation process, the heat transfer between the airstream and the surrounding is negligible. So the next one is as for the large building process. Previously we have seen that for the cooling process, you require a cooling coil or cooling section, where in our environment, for example, when the temperature is about nearly 40 degrees Celsius, and then when you want to drop it to 20 or 25 degrees, 18 degrees Celsius, for example, so from 40 degrees to 18 degrees, it will cost a lot of energy, because the delta temperature, delta T, is about 22 degrees Celsius. So if you imagine that the energy consumption that required, which is Q equal to M dot times with the delta T, where the delta T is already about 22 degrees Celsius, which is if we can reduce the inlet temperature from let's say that from 42 or 40 degrees Celsius down to, let's say that, about 30 degrees Celsius, so which means that the delta T value will be getting smaller. So when the delta T is smaller, your value for the amount of the heat that has to be absorbed from the cooling section will be getting smaller. So how we can do this, which is actually we can do like recirculating the process of air that have been treated in the environment, in the building, and then recirculate into the cooling sections. So for example, if I draw this one here, so for example, you have this cooling section passing through this one, and then let's say that from the environment 1 to environment 2, the temperature has been dropped, let's say that about from 40 degrees Celsius to 20 degrees, so 20 degrees Celsius, okay? So 20 degrees Celsius, and then this is passed through the your AHU unit, okay, go into the building and then take out the heat, and then let's say that this is going to be about 30 degrees Celsius, okay? So from this 30 degrees Celsius, it will add with the surrounding air, which is coming at 40 degrees Celsius, okay, and then treated into the adiabatic mixing, and then go into this So this is a state 1, that's state 2, state 3, and then this is a state 4, and then passing into here, and then will be cooled into the next section. So which means that the amount of the heat that can be absorbed from here is much smaller than the amount of the heat that has to be absorbed when it is only from 40 degrees Celsius to 20 degrees Celsius. So as comparing with 30 plus 40, and then this is some of the air stream coming in. Okay, so the amount of the heat that has to be absorbed in this position will be smaller. So it will reduce the energy consumption for the building. Okay, so through this through these processes, the mixing region is assumed to be adiabatic, which means that there is no heat transfer between the air stream and then the surrounding environment. And as well, if you do the mass balance and energy balance for S stream 1 and S stream 2, okay, which is S stream 1, M dot A1, M dot A2, and then this is output, M dot A3. So what we have here is that the mass balance for the dry air, M dot A1 plus M dot A2 equal to M dot A3, and the mass balance for the water vapor, M dot V1, M dot V2, M dot V3, which is given by omega 1 M dot A1, omega 2 M dot A2 equal to omega 3 M dot A3. And finally, the energy balance, H dot 1, H dot 2, and H3, which is the energy balance involving in this adiabatic mixing region, mixing conditions. So with this, what we can do is that from the energy balance and mass balance, the whole detail I have derived in your in my YouTube channel, so you can refer to the YouTube channel. But by the end, the mass flow ratio between the inlet 1 and inlet 2 can be presented by this correlation, which is the difference of the relative humidity, specific humidity of the inlet and outlet, and then as well the difference of the delta H, or the difference of the enthalpy, which is presented by this one. But actually this is relative. Yeah, it depends on how you evaluate your your schematic diagram for this layout. So you don't have to remember this equation, but the most important thing is that you have to understand how to derive, how to do the mass balance and energy balance, and come up with the correlation between the mass flow rate of first stream and then the second stream. Let's look at the example. Previously I put this as 1 atmosphere, but which is actually, when we are using with the 1 atmosphere, it is quite easy for you, because you just need to use with the psychrometric chart to obtain all the values related to the parameters or variables available. Okay, so let's look at this example where we have a saturated air, which means that the Phi is equal to 100%, or the relative humidity equal to 100%, leaving the cooling section of an air conditioning system at 14 degrees Celsius. Okay, so state 1, T1 equal to 14 degrees Celsius, Phi1 100%. So if you use a psychrometric chart, then you can read directly the specific humidity and the relative humidity at the rate of 50 meter cube per minute. Okay, so it is mixed adiabatically with an outside air, at 32 degrees Celsius and 60% of the relative humidity at the rate of 20 meter cube per minute, assuming that the mixing process occur at 100 kPa. Okay, later on, you just use this example and then change it to 1 atmosphere and then just use with the psychrometric chart. Yeah. Okay, from here, if we sketch a schematic diagram, okay, if we sketch a schematic diagram, so this is a schematic diagram. Yeah. So this is a schematic diagram. Okay. So this is a say state 1, and this is a state 2, and then come up with the state 3. Okay. All right. So at the state 1, volume flow rate V equal to how much before? Lupa dah saya. Berapa tadi? 60 40?
50 meter cube
50 m cube per minute. Okay. And then T1 equal to 14 degrees Celsius. V1 100%. Okay.
Oh, dia saturated air.
Yeah, saturated air. So P is equal to 100%. Okay. And then at the state 2, V dot 2 equal to 20 meter cube per minute. And then T2 equal to berapa? 30 32 degrees Celsius. And then P2 equal to 60%. Yeah, betul. Okay. And then now we need to determine V dot 3, M dot A3. Okay, yang ni pun sama. M dot A1, M dot A2, omega 2, omega 1. Okay. So we need to determine the temperature T3, omega 3. Lagi apa? V3. Yeah, V3. Alright. So if we sketch a psychrometric chart, what we can see here, even though it is cannot be used with a psychrometric chart, but it's good to view the processes what we're going, so that you can imagine that the process going to happen and then expect what going to happen there. So the dry bulb temperature here 14 degrees Celsius. Okay. V equal to 100%. So this is a state 1, and then mix. So this is a state 2. Okay, which is we don't know. Sorry, this is a state 2, 32 degrees Celsius. Okay, and then the relative humidity is 60%. Yeah, and then it mix, and this is a state 3. Okay, this is a state 3. Okay, so alright, something like that. Yeah, omega 2 is omega 1. Okay, so we need to determine or calculate all the variables and parameters at the respective state. Okay, so as for the state 1, so buka you punya psychrometric property table ya. Buka property table siap-siap, pergi pada table steam table. Ya, buka pada steam table. Boleh? Idea? Afiq, tolong Syafiq, tolong pergi pada property table. Okay, so at the state 1, V1 equal to 50 m³ per minute, which is equal to berapa tu? Dalam okay. Sebelum nak cari ni, kita kena dapatkan the value for m dot a. Okay, we need to get m dot a. So which is m dot sama dengan the mass flow rate, m dot equal to rho kali dengan v dot. Okay, rho kali dengan V dot. M dot A, rho A, V dot. Which is, if we look here, rho A kita tak ada lagi the value, which is rho A equal to, if we use ideal gas equation of state, PV equal to P equal to rho RT kan. Okay, which means that rho A over RT. Okay. So in here, what we have, PA, RA, T. Okay, so T temperature dah ada value 14 degree Celsius, which is PA. Well, so that we need to find the PA, which is relative humidity is equal to PV over PG. Okay, where PA is equal to P minus PV, which that P minus P PG. Okay, for phi equal to 100%, PV equal to PG, which is equal to 100 kPa minus berapa? At 14 degree Celsius, nilai PG dia. PG at 14 degree Celsius. Berapa nilai PG dia? Cuba tengok. Boleh? Somebody? Tolong?
Ya, saya kena balik.
Tengok pressure dia.
Ya.
Satu rated pressure dekat 14 degree Celsius.
Dia tambah tu bagi 2 je kan?
Apa dia?
Sebab dia 10 dengan 15 temperature.
Oh, antara 10 dengan 15 degree.
Ha.
Okay, kita tukar jadikan 15 degree. Jadi 10 degree. Susah sangat. Ya?
10.
Jadi 10.
10 1.2281. 1.2281.
1.2281 kPa ya. Okey, jadi berapa tu?
Ya. 98.77.
37
77 sir.
98.77 kPa ya. So which mean that our, sebenarnya boleh kira masukkan dalam tu terus tau. Which is M dot A equal to PA. Okay, PA berapa? PA 98.77 bahagi dengan KPA tau ni, KPA. R kalau you nak bahagi dengan boleh juga. R untuk ini sama dengan 0.287 kilojoule per kilogram Kelvin. Okay, and then darab dengan temperature 10 campur dengan 273. Jadi berapa? 283 kan? Okay, so MA1 dia boleh dapat value berapa tu?
$1.2161. Sir?
Ya, berapa?
1.2161.
1.2161 ya. Kilogram per second. Okay, ingat ni value ni. Saya takut lupa nanti. Okay. Lepas tu you kena kira pula the value for the apa ni? M dot A. Okay, M dot A then omega. Omega 1 sama dengan apa? Omega 1 sama dengan MV over MA1. Itu tak boleh juga kan? So apa you kena dapat, you kena dapatkan daripada yang ini. Okay, sorry. This one you cannot use this equation. you kena gunakan equation omega 1 equal to 0.622 PV over P PA. PV over P.
Bukan over P tolak PV1.
Ha?
0.622 PV over P minus PV1.
PV over PA.
Okay.
PA sama dengan P minus PV. Sama juga ya.
Okay.
Which is equal to 0.622. Berapa tu? 622. PV tadi berapa? PV sama dengan PG kan? 1.2881 kan? 1.2281 bahagi dengan
98.77
ya. Okay, which is sama dengan berapa tu?
Satu.
Berapa?
0.00773
Kali 1000? 0. Tak apa, 0.
00773
Okay, kilogram of H2O over kilogram of dry air. Okay. So omega 1 dah dapat, okay, so yang ni H1 pula. H1 equal to berapa? CPT plus omega 1 Hg at 1. Okay. Which is equal to CPT berapa? 1.005 kilojoule per kilogram degree Celsius. Kita ambil yang ni je, which is 10 degree Celsius plus omega 1 0.00773. Lain semua tulis ya. Calculate nanti responsif dalam kelas. Hg 2500.1 plus
2519.2
value dia kat situ. Okey, tak payah dia nak tulis 1.82 kali dengan temperature 10. Okey, alright. So jadi total dia berapa? 10.05 tambah dengan 0.00773 2 berapa tu? 25 19.72 okay. So you calculate then dapat dah H1. Okay. 29.52 kilojoule per kilogram. Okay. So catatkan all the values ya. Okay. At state 2 M dot A2 sama dengan rho A2 kali dengan V2. Okay, sama juga calculation dia. Rho you kena dapatkan nilai PA. Okay, PA is equal to apa dia tadi? PV ya. PA sama dengan P minus PV, where PV is equal to berapa? 32 degree Celsius ya. 32 degree Celsius ada dalam note tak? Ada dalam table tak? Tak ada ya?
35.
Okey, kita tukar 35 degree ya. Okey. Tukar 35 degree Celsius. Okey. Change to 35 degree Celsius. Okey. So which is PV? We know that PV is equal to P kali dengan PG at 35 degree Celsius. Okay. So PV sama dengan ni 60% kan, 0.6. PG at 35 degree Celsius berapa nilai dia?
5.6291.
5.691 KPA.
6291.
6291. Okey. So jadi berapa tu nilai dia?
3.377.
Ha?
3.377.
3.377. Okay. Alright. So our PV 2 and then our PA 2. So our PA is equal to 100 KPA minus 3.377 KPA. Dapat berapa tu?
96.623.
96.623 KPA ya.
Okay.
Alright. So M dot itu equal to 96.623 over 0.287 kali dengan temperature T2 35. 35 campur dengan 273 berapa? 35 campur 273 308 kan? 308. Okey, berapa tu? Berapa? Satu point? Huh? 1 point? Oh kali. Ada kali dengan tu tadi tak? 20 V dot tadi. Ni kan?
Belum.
Okey, V dot. Tadi pun ada calculate ni tak tadi? Lupa nak tanya tadi. Bahagi dengan 60. 20 M cube per minit kan? Bahagi dengan 60. 1 minit sama dengan saat. Okey, 60 saat sama dengan 1 minit. Okey. You kena bahagi ni dulu. Then you will get the M dot value. Berapa ni? Tadi pun sama. Sebab unit dia dalam apa nama tu, dalam ni ya, dalam per minit ya. Okey. Okey, berapa dia?
.364 je.
3643 kilogram per second.
Minit second.
Okey. Yang previous tadi pun you kena re-evaluate balik dia punya calculation tu. Boleh? Tengok balik. Ataupun you dah kali dah tadi nilai M dot A. And then omega 1. Okay, omega 1. Omega 2 sama dengan 0.622 PV 2 over P PA2 which is sama dengan 0.622 darab dengan berapa tadi? 3 point berapa?
377
over 96 point something kan, 96 point
6.63.
okay. Then you will get the value for this one. Okay, omega. Okay. Alright. Okay. So berapa?
0.0217.
Okay. Kilogram H2O over kilogram dry air. Right. So omega 2 H2 sama dengan Cp T2 plus omega 2 H2 sama berapa ni? 2501.3 09 something like that. Lupa. Nanti you tengok balik equation.
2501.3
1.82 T2 which is 1.005 kali dengan 35 degree Celsius plus omega 2 0.0217 2501.3 plus berapa tu 2501 plus 1.82 kali dengan 35 degree Celsius. Okay, so then you will get the value. Berapa tu?
$90.938 kilojoule per kilogram.
Okay, good. Alright, so berdasarkan daripada sini, from here we can calculate the we can do the analysis for the adiabatic mixing regions. So for adiabatic mixing, okay, so we do the mass balance. Okay, where m dot A1 for the dry air, yeah, for the dry air, m dot A1 plus m dot A2 equal to m dot A3. Then you boleh calculate terus lah actually berapa nilai dia. Okay, which is you masukkan value tadi, boleh tak? Okay, and then mass balance for the moisture ataupun water vapor, which is m dot A1 omega omega 1 m dot A1 plus omega 2 m dot A2 equal to omega 3 m dot A3. Okay, alright. So m dot A2 you boleh dapat daripada sini, m dot A3 boleh dapat daripada sini, Okay. So which is omega 1, tak kira pun tak apa sini kan, tak kira, okay sorry, omega 3 you kena dapatkan. Okay, so omega 3 sama dengan From here omega 3 is equal to omega 3 sama dengan omega 1 m dot a1 plus omega 2 m dot a2 divided by m dot a3. Okay. Boleh dapatkan. Okay. And then energy balance. Okay, energy balance. Energy balance. Energy balance. M dot A H1 plus M dot A1 A2 H2 equal to M dot A3 H3. Okay, so H3 is equal to M dot A H1 plus M dot A1 A2 H2 over M dot A3. Okay. Boleh kira ni? Sekejap. Saya tunggu kamu kira. Berapa tu? Hello? Hello? Aidil?
Ya, sir.
Okey. Kira tak? Omega 3 berapa?
Omega 3 0.109.
0.
kot.
Sorry. M dot A3 dulu. M dot A3 berapa? M dot A3?
1.5804.
1.5804 kilogram per second. Okay. Omega 3 tadi berapa? Omega 3?
0.0
0.01
09.
109 ya. Kilogram H2O over kilogram air. Okay. H3 sama dengan berapa? H3 berapa?
.67.
43.67 eh. Okay. Right. Kalau you gunakan, this is if you use with the psychromatic chart kalau gunakan at 1 atmosphere. So but actually untuk continue yang that previously, the value untuk omega 3 dapat, cumanya value untuk temperature dengan relative humidity. Okay. So temperature you boleh dapat daripada how to get the temperature. Temperature you boleh dapat daripada this value, which is nilai HA. The temperature you boleh dapatkan daripada value untuk HA, which is H3 equal to CP T3 plus omega 3 apa ni 2501.3 plus 1.82 temperature T3. Okay. So H3 tadi berapa? 45.63 kan? 45.63 CP 1.005 T3 campur dengan omega, ataupun otherwise you boleh buat macam ni pun tak apa. Boleh juga. H3 berapa? H3 minus CP T3. Oh, okay. Tak, like this. Which is CP T3 plus omega 3 2501.3 plus 1.82 T3 omega 3. Okay. So H3. So you reorganize balik equation ni. H3 minus omega 3 2501.3 sama dengan CP3 CPT3 plus 1.82 omega 3 T3. Okay, which is T3 CP plus 1.83 kali dengan omega 3. Okay, which is T3 sama dengan H3 omega 3 2501.3 over CP plus 1.82 omega 3. Boleh? Which is equal to 45.63. Tolak omega 3 berapa tadi? 0.01 berapa something you tengok CP
0.0109 je.
Okay. Okay. 0.005 plus 1.82 kali dengan 0.00109 kan? So dapatlah nilai T3. Yep. Okay. So I show you the example. Yang ni jalan dia lebih panjang lah actually. Tapi but if you just use with the psychromatic chart, then it is very easy. Okay. Especially kalau you derive the mass balance and energy balance before, and then you akan dapat teruslah macam mana that equation should be. Okay. So berapa nilai T3 kita tu? Hah? Rendah
Salah.
Tapi okey juga 32 sebab dia punya mass flow rate tu agak tinggi daripada satu punya conditions tu. Okey, betul.
17.92.
Okey, 17.92 ya. Relative humidity macam mana nak dapat? Relative humidity V2 sama dengan apa? V2 sama dengan macam mana nak dapat V2? V2 sama dengan apa? PV over PG at values kan? At 17.92.
Kenapa cari kat V2 Sir? V2 bukan dah ada. V2 dah ada kan?
V3. V3. You tengok dekat 18 lah actually. This one tengok dekat 18 lah. Which is about 18 degrees Celsius lah. PV tak ada. So macam mana nak dapatkan nilai PV? Okay, omega kan? Omega 3 sama dengan 0.622 PV over apa? PA kan? P minus PV. P minus PV. Betul tak? So which is actually kalau you reorganize the equation, P minus PV omega 3 equal to 0.622 PV. So you expand this equation, then you akan dapat the PV value. Ya?
Kalau guna formula lagi satu tu tak valid untuk soalan ni.
Yang mana formula lagi satu? 0. berapa? Ada juga boleh. Yang ada omega ya? Yang ada omega tu.
Yang ada ni V equal to omega darab P bagi dengan 0.622 tambah omega dalam kurungan P.
Boleh juga. Tapi apa? Dalam kurungan apa?
Dia
dalam kurungan apa?
Ya.
Tengok equation tu ada cukup tak? Kalau equation tak cukup, values, parameters, variables cukup ke tak cukup? Tak kisah apa pakai formula mana-mana, tapi the thing is that you have to come up dengan this one. Ya? You nak pakai
omega.
Sekejap ya, berapa tu? Nak padam ini. Omega. Okey, omega.
Omega darab P.
Omega darab V.
Darab P total.
P. Omega P bahagi berapa?
Dalam kurung 0.622.
Okey.
0.622
okay. Tambah omega
dalam kurungan PG.
PG at 18 degree Celsius ya. Boleh juga macam ni. You boleh dapat direct equation lah. Sama je. Okay? Sama je macam equation yang saya dirah tadi tu. Kan? Lebih kurang je. Tak? Ya, the important is saya sebenarnya saya tak suka hafal equation. Ya? I prefer you untuk fahamkan the situation yang involved with that problem. That will be better lah. Okay? Alright, so the next one, you the equation tadi tu, the problem gunakan untuk dapatkan gunakan with the psychromatic chart. Okay, so this is assignment 3. And lastly with the wet cooling tower. So saya rasa wet cooling tower ni saya tak derive on the whole detail the derivation untuk that example lah. So the wet cooling tower ni, if you go to the engineering complex building, what you see is that of course yang besarnya air conditioning processes lah, tapi on the rooftop that you're going to see some of the wet cooling towers. So the wet cooling tower, the function of the wet cooling tower is to produce the water. So there are two types of the wet cooling towers. One is the forced wet cooling tower yang gambar tadi, and another one is the natural draft cooling tower. So this is the function dia untuk hasilkan the cool water. So with the natural draft, the chimney dia tu agak tinggi. Okay, so kenapa tinggi? So because it is naturally because to produce the pressure difference antara yang bahagian bawah dengan atas, so there is no fan yang terlibat. So the air movement is due to the pressure difference. So pressure difference bahagian atas lebih rendah, so berbanding dengan bahagian bawah, so it create a natural draft punya movement. And then air yang masuk daripada bahagian bawah lebih panas berbanding dengan atas. And then the warm water which is injected daripada heat exchanger. Okay, so this warm water daripada heat exchanger. So daripada mana warm water ni datang, which is heat exchanger that is connected to the chiller. So the function of the wet cooling tower is to produce a cool water so that it will go to the heat exchanger of the chiller. So this heat exchanger will take the heat from the condenser of the chiller. Okay, so macam you buat dalam you punya lab ya. So in your lab MEC 554 lab for the refrigeration cycle, you ada nampak there is two ways for the condenser and evaporator. So one, the condenser is running with the natural draft just with the air, and another one, the condenser that is running with the heat exchanger that operate the heat exchanger for the condenser is cooled down by the cool water. So yang inilah yang berlaku that which is actually just to show you how the operation of the chiller dalam actual condition dalam industri, that the chiller is the heat daripada condenser been absorbed by using this cool water from the chiller. Sorry, the cool water from the wet cooling tower. Yeah. So this is an example. Saya rasa tak sempat nak bagi example kat you all ni. So cuma you boleh refer kepada di reference textbook lah yang saya bagi ya. So dalam tu ada example for this one, which is actually sama je. Cuma the thing you have to do the mass balance and energy balance. So this is the key point dia, mass balance, which is mass balance for the dry air and mass balance for the water. So kalau you tengok tadi, this is the natural draft kan, macam tu, and this is yang masuk, and then this is the water. Sorry. Okay. So this is a sprinkler. Okay. So this is air. Let's say the air masuk 32 degree Celsius, and then this is a warm water, M.W1. Okay, kita buat 1, 2, and this is state 3, and then this is yang keluar ni cool water. Okay, so M humidifier kat sini disejukkan daripada air yang coming and then dia akan produce the saturated condition. This is a T2, V equal to 100%, and then dia akan sejukkan which is a drop of water kat sini. Okay, so let's say that the cool water 1, 2, 3, and then this is going to be state 4 lah. Okay, W M.W4. Okay, so let's say that M.W4 dia keluar dekat T4 equal to 20 degree Celsius, 60, yang ni keluar let's say 35 degree Celsius, V equal to 100%. Hot water, let's say that dia masuk dengan let's say 35 degree Celsius. Okay, cool water let's say 18. Okay, So if you use the mass balance and energy balance, masukkan semua and energy balance. Mass balance untuk dry air yang masuk 1 m.a1, yang keluar m.a1, lepas tu yang drop sama je, m.a1 sama dengan m.a2. So constant for the water yang masuk daripada yang ini m.a1 omega 1 plus m.w3 equal to yang exit pula m.a2 omega 2 plus m.w4. Okay, so that is a mass balance. Energy balance m.a h m.1 h1 yang masuk plus m.w3 h3 equal to m.a2 h2 plus m.w4 h4. So you will solve the equation, do the mass balance and energy balance, then you will get all the requirement. Yeah. Okay. So kelas kita pun dah 15 minit dah terlebih. So any